we're going to talk about the physical characteristics of gases, not how they behave chemically. This is purely their physical behavior as a separate state of matter. Chapter 11 is where we started to get into the actual chemistry and stoichiometry of reactions involving gas. But this is all their physical characteristics, which, like I said, you did in physical science. This is a condensed, abbreviated version of our normal trip through this material. Kinetic molecular theory of matter, you already know. This is what you have been learning about matter since the first time anybody in a science class said anything to you about matter. All of you take for granted, as a matter of course, that everything you've ever touched in the world is made up of tiny particles that are vibrating, yes? Yeah, that's what matter is. Tiny particles vibrating. The hotter something gets, the what it vibrates. Faster. The colder something gets, the slower it vibrates. That is all that kinetic molecular theory of matter is. That's it in a nutshell. You already know this. What you didn't have previous to this was the scientific name of the theory. Okay? This is a theory. This is a scientific theory just like the theory of biological evolution, theory of gravitational attraction. What that means is that all observations we have support this. This is not in any way controversial. There is no like opposing hypothesis to the kinetic molecular theory of motion. There are no credible and reproducible results which do not support the kinetic molecular theory. I'm sure some interesting person, I was going to use a less flattering term like crackpot, out there has done something that they claim says something else, but credible and repeatable are important here when we're talking about what is science. So within the kinetic molecular theory of matter, one of the things that we're concerned with in this chapter is ideal gases. Now, ideal gases exist the same way ideal teenagers do, or ideal adults do, or ideal German Shepherd puppies do, or ideal anything else does. Ideal best friends, ideal siblings, ideal whatever. Not so much for real. But we can talk about them and pretend that they're perfect. If we have what we're calling an ideal gas, it behaves absolutely perfectly in accordance with all the things that we could say about how a gas should behave. We'll talk about the reality a little further down the road. There are no deviations. There are 5 assumptions. When we talk about kinetic molecular theory and gases, there are 5 assumptions that we're going to look at. And we're going to truth meter them from 99% truthful to somewhere in the middle. Okay? So these 5 slides I've sort of put together into one just so that we can go through them relatively quickly. The first assumption, gas particles are really far apart. So I would like you all to take your hands, put them up in front of you, and do this. Hit the air in front of you. Why would hitting your desk hurt your hands, and yet smacking the air does not? You're hitting molecules of matter either way. Okay, right. Gases are large numbers of particles, but they're really spread out. There's a lot of space in between them. A lot of the space that's taken up by a gas is actually empty space. So those molecules are very spread out. This is also why we can compress a gas. If you've ever pumped up a bike tire with a foot pump, you have compressed gas yourself. If you've ever ridden in a vehicle with air-filled tires, you have ridden around on little containers of compressed gas. So that one, truth meter, 100%, yeah, that's true. Gases do consist of large numbers of particles spaced pretty far apart. So that one we're solid with. Number 2, this is a little bit more questionable. We know that particles are vibrating. Particles can collide with one another. And the particles in gases are moving around. They're flowing all over the place. If we're talking about an ideal gas, what we assume is that when 2 particles collide, boom, they both have kinetic energy because they're both moving. When they collide, no kinetic energy is lost. Now, in reality, if you think about playing pool, I think probably most of you have either played pool or seen pool played. When one pool ball strikes another pool ball, the one that, if you have a not moving ball hit by a moving ball, this one speeds up, this one slows down. But the total kinetic energy is a little bit less than there was, because there's some loss of energy to noise, to light, to friction, to all these other forces. So we experience this overall slight reduction in energy. What we pretend when we talk about ideal gases is that there's no loss. That two gas molecules can bump off one another and there's no loss of anything, that they can smack off the side of a container and there's no loss of energy. That's not really true. So that one's, I'm not enough of a physicist to give you a percentage truth on that. I'd say 50 to 75. There is some small loss of energy, but not a lot. Not a lot. So that one's a little shaky. Number 3 really probably should be number 2, but it's not. So gas particles are in continuous, rapid, random motion and therefore have kinetic energy. Well, yeah, that's true. That's absolutely true. And that's kinetic molecular theory for everything. All particles are in motion. All particles have some amount of kinetic energy. It's the energy that they have because they're moving. What KM says about ideal gases is that their kinetic energy is high enough that if they do hit one another, that energy is enough to move them past one another. They don't stick together. They don't clump up because they strike. 4. This one is a little bit shakier. No forces of attraction or repulsion between gas particles. When gas particles collide, they immediately bounce apart. So I don't know if you're aware of this. I don't think that you do theory of gravitational attraction in physical science. Here's what I'm going to tell you, and it's earth-shattering. Any two objects that have mass, even single atoms, have an attractive force between them. If I sit you up an inch from your buddy, you have an attractive force towards their mass. Their mass is attracted to your mass. Your mass is attracted to their mass. Whoa. So the next time that you're like crowding your sibling intentionally just to irritate them, you can say, my mass is just attracted to your mass. It's science, I can't help it. And then you can smush them into the side of the seat or something, something equally distasteful. Why don't we actually experience this on Earth? Because there's something even more massive that we're all being attracted to continually. It's under your feet. The Earth is so massive, the attractive force of Earth for you and you for Earth completely blots out. It's like so the attractive force between you and any other piece of mass on the planet is like taking an Olympic-sized swimming pool full of black paint and putting in one little tiny drop of white paint and saying, can you see it? No, you can't see it. That's the attractive force of, these two pens for one another compared to the force of the Earth. Totally overwhelmed, totally invisible. But there are some small gravitational attractive forces. Now, out in space, where you're away from the influence of a planet attracting, two objects like this put side by side would become attracted, would move towards one another because of mutual gravitational attractive pull. So this is shaky, okay? That one's not really true, but on Earth it pretty much works out that way. Number 5 is another one that's pretty true. So kinetic energy, is the energy of things that are moving. Gas particles are moving, they have kinetic energy. What did you all say about if you get it hotter, it moves faster. If you cool it down, it moves slower. Well, it turns out that temperature is just a proxy for kinetic energy. So temperature is just a way of us measuring the kinetic energy of something, but not using the units for kinetic energy, using sort of a proxy for that. So we can write a formula for kinetic energy, Ke equals 1/2 mv squared. And what we can say is that two things that are at the same temperature have the same amount of kinetic energy. Well, if they have the same kinetic energy, but they have different masses, they have to have different velocities. So really all this boils down to is heavier particles move more slowly at the same temperature than lighter particles. My favorite image on this, a school bus full of cinder blocks versus a Honda Civic full of cotton balls. One of those things moves a lot faster than the other. The Honda Civic can zip around. You're going to be hard-pressed to get the school bus full of cinder blocks up to 100 miles an hour. The Honda Civic, no problem. Okay, so smaller, lighter particles at the same temperature move faster than heavier, larger particles. And that's true. That's not fudgy, that's not shaky ground at all. That's true. Okay, so that's our 5 assumptions. Questions, comments, concerns. The next 4 chunks of information. These are really just things that describe how gases behave, but they describe them in the light of kinetic molecular theory, chem. So all of these, when you were doing your close reading, you probably thought, well, duh. Gases fill a container. Gases don't have a definite shape. They don't have a definite volume. Whatever container you put a gas in, it will expand to fill it. They are expansive. Fluidity. This I think you have heard, but I want to double check with you. Fluids are any phases of matter that are capable of sliding past one another. So liquids and solids are both fluids. Their molecules are not locked in place. They can slide, liquids and gases. See, there was my April Fool's joke. Liquids and gases are both considered fluids. They both flow past one another. And that's just kind of duh. Low density and compressibility. Well, we just talked about that. Gases are really, really, really not very dense at all. And because of that, you can compress them. You can make them more dense. You can push more gas into the same volume and compress it. Now, these 2 are the ones that may not have been a duh for you when you looked at the chapter on your own. So diffusion. If I have, this could be a room, this could be a container, this could be anything, and I release a little bit of some kind of material, like let's say I spray perfume over in that corner. Who's going to be the first person to smell it? I will. I sprayed it. I'll be the first one to smell it. I sprayed the stuff. Who's going to be next to smell it? I'm spraying it from that corner. You and Jonathan. Who's going to be last to smell it? Yeah, Sam and Madison probably. Maybe Ashlyn. Maybe Jacob. We'd have to get out a tape measure to prove it. You all know that. That's instinctive. So the idea that any fluid material moves from an area of high concentration, so in this case, where I sprayed that perfume, out to areas of low concentration, has a name. You learned it in biology. It's diffusion. So fluid particles will diffuse into one another. And eventually, and they diffuse until they're all evenly distributed throughout whatever system they're in. So eventually here, that perfume, the odor molecules that you're smelling would be so spread apart that any one good sniff probably wouldn't get you any odor particles. We wouldn't smell the perfume anymore. Okay, that's, odors fade because the odor molecules diffuse throughout a room or a system or whatever, and then we can't smell it anymore. So that's diffusion. And the big thing to know about this is that the rate of diffusion is all about the speed of the particle. So the rate of diffusion is all about the speed of the particle, and what controls the speed of the particle? It's mass. It's mass. At the same temperature, a more massive particle moves more slowly. So, natural gas, CH4, odorless. But if you inhale enough of it, it will kill you. That's not good. Nobody wants a gas leak in their house. Because it's odorless, you can't tell if there's a gas leak. So they add a chemical to natural gas. It's a chemical compound. They're mercaptans. It's a class of chemicals that are added to natural gas. Now, natural gas is CH4 and C2H6. Those are both really light little particles. What would be important about the mass of mercaptan? What would you want to make sure that whatever you were adding as a smell agent, what would you want to make sure of about its mass? Okay. Yeah, because particles diffuse, their speed of diffusion is based on their mass. So if you've got something that's allowing people to detect a natural gas leak, you want it to be pretty similar in mass to the natural gas particles. Okay, so a lighter gas will diffuse faster than a heavier one. So if you've got two gases that you want to diffuse at the same rate, they better be similar in mass. So and I actually would like to look up mercaptans. They have to be similar in mass to natural gas. Effusion is a little bit different than diffusion. So diffusion is a fluid moving through a system until it's all evenly distributed. Effusion is when we have specifically the movement of a gas through a narrow opening. So you have, how many of you have ever gotten a latex balloon? Goes in tight. That's so sad. Only 2 of you have ever gotten a balloon in your lives? I'll bring you balloons. Okay. I'm sorry, Kira. I'll bring you a balloon tomorrow. The grocery store near my house gives them out for free. So, does your little latex balloon that you take home look the same 2 days later? No, my daughter's finding this out very sadly. She gets very sad every time 2 days later. Why is the balloon like that? And I tell her, it's effusion. There are little tiny holes in the balloon, and they seem tiny to us, but they're bigger than the gas molecules that are inside the balloon. So the gas escapes through the little tiny holes. It's called effusion. Sigh. Anyway, the smaller, the lighter the molecule, the faster they effuse. So, same thing as diffusion. The faster the molecule is able to move, the faster it is able to effuse. Effusion occurs in lots of settings. Balloons are a good example. A membrane with a single opening in it is another example. So anything where you have some barrier and a tiny opening, and gas particles are able to travel back and forth across it. So, again, directly proportional to the velocity of the particles. Velocity of the particles is directly proportional to mass. Okay, that was a lot of stuff in a short period. Any questions? Here's the shocking part. Real gases, just like real teenagers and real, lab puppies, don't actually behave perfectly. They don't quite meet everything that we said about them. A lot of it. So, you're going to enjoy this. You're going to like this. 1873. Dutch chemist named Van der Waals. You all want to say this, I know. It's Dutch. So the V has an F sound and the W has a V sound. So everybody says Van der Waals. It's not Van der Waals. It's Van der Waals. Come on, with me. 1, 2, 3. Van der Waals. Did you just say Van der Waals? Okay. We'll do it faster so that you can all start on time. 1, 2, 3. Van der Waals. Good job. Van der Waals. Isn't that fun? Don't you feel better now? No? Not so much? Okay. Well, anyway, what he noticed was that there were little forces between particles of gas. Shh, we won't talk about it. We just won't tell anybody it's happening. Shh, which is pretty much what we do. We pretend it doesn't happen. It doesn't happen a lot. So, and we will talk later about Van der Waals forces, which were discovered by Van der Waals, and we're hinting at here. The place that we see this the most, For the most part, yes. Gases do behave close to ideally. Where we see the big deviation, if they are under really tremendous pressure. What does pressure do to a gas? Pushes the molecules closer together. Well, if there are little attractive forces between the molecules and you get them real close, that's the point at which they can reach out and sort of grab a buddy. The other place that you see this is at very low temperature, because the colder they get, the slower they move. So if you're moving past one another really fast, there's almost no time for those attractive forces to kind of go and grab on. But if you're pushed really close and you're moving really slow, then there's time for those little forces to arise between them. So we mostly see this at high pressure, low temperature. At normal room temperature, we don't see an issue with them deviating much from ideal behavior, but really the ones that act the most like ideal gases are things like noble gases. There are almost no forces of attraction between noble gases and anything, and at normal atmospheric conditions. So regular pressures or low pressures, regular temperatures or even higher temperatures. So, if you've got gases that have some attractive forces anyway and then you put them at high pressure, low temperature, that's when you really see issues cropping up and they do not behave ideally. It's not a big deal. Okay. Dun da da dun da da dun dun ch. Dun da da dun da da dun dun ch. Come on. Dun da da dun da da dun dun ch. Dun da da dun da da dun dun ch. Wham! I throw a ball of ideal gas at you. Okay. Under pressure, dun da da dun dun ch. Dun. No. Bowie. Come on. You gotta love Bowie. Someday I'll have a way to link this into this and it'll just play and I'll be really happy, but I don't know how to do that yet. So anyway, if anybody wants to teach me, they can. Pressure! Do any of you feel like you're under pressure? Yes. I'm glad you said that, Sam. What's pushing you down? What's keeping you down? Gravity. Okay, well, there's the attraction that the Earth feels for you and that you feel for the Earth. That keeps your feet on the ground. But what's pushing you down, grinding you into the surface? It's not the man.
Atmospheric pressure.
What's atmospheric pressure?
Pressure by gases.
What does that mean? So, I would like you all to stand up. So, pressure is force per unit area. Now, everybody look at your thumbnail. Unless you have a freakishly large or freakishly small thumb, your thumbnail is about 1 square centimeter. And the atmosphere, we never did say what was pushing down on you. I want you to imagine, look up. Okay, you see the ceiling. But imagine you can look beyond the ceiling, beyond the roof, up into the clear blue, beautiful sky. And up above you is a cylinder, the same size as you, because you are roughly a cylinder, about 10 miles high, full of gases. And gases, my dear, have masses. Gases have masses. So 10 miles or so worth of gases pushing down on you. Whew. I didn't fall over, though. That was good. Why don't you feel that? Why don't you feel 10 miles of gas pushing on your head? Because in reality, you don't feel it. Woo! I can dance. Yeah, you can. You don't feel 10 miles of gases pushing on you. Why not? Anybody ever see images of the early sea creatures that were brought up from the bottom of the ocean? In the history of deep sea exploration, it's fascinating. The first ships that were capable of doing sampling of deep sea environments would bring up sea creatures from the deep sea with dredges. And when they got those deep sea creatures up to the decks of the ships, you know what happened? They exploded. Literally. They blew up. They popped. They just went, and it was a bloody mess. Literally a bloody mess. You'd be a bloody mess too. Yeah, because deep sea creatures not only have that 10 miles of atmosphere pushing down on them, they've got 3-5 miles of ocean water pushing down on them. And their bodies have evolved to live under that kind of pressure, which means the pressure on the inside of their bodies that's pushing out against all that pressure pushing in is really high. So when you bring them up, they go, and they literally burst in a bloody mess of goo. It's disgusting. We have better ways of sampling them now. Whew, thank goodness. You have evolved to live under the pressure of the atmosphere on this planet. If we take you out into space and we suddenly remove all that pressure from you, guess what happens? Yeah. Actually, you instantly boil. You don't even explode. All of your... Pardon? No, but I will. I think there's a lot of bad science in that one, though. Anyway, you literally, all the forces that are holding you together as a solid with liquids inside you just go away, and then you turn into a vapor. Poof. You're done. You boil. All of you turns into a vapor, and you are stardust floating in the atmosphere. That wouldn't be a bad way to go, I guess. It'd be pretty fast, I think. But, yeah, you have evolved. This has taken some strange turns today, hasn't it? You have evolved to live under this amount of pressure. This amount of pressure of 10 miles of atmosphere pushing down on your body at all times. We call it atmospheric pressure. It is actually the pressure exerted by that 10-mile, and I'm making up that number, but it's close, that big column of gases that's pushing down on you. And we can measure it. So at sea level, ooh, somebody left me a pen. Atmospheric pressure is about 10 newtons per square centimeter. So I want everybody to take a spring scale with a buddy. Take a spring scale with a buddy. Now, we established what a square centimeter is like, roughly. Pass those around. So everybody in a buddy has a spring scale. Oh, no. We should have 6 of them out. So we have 12 of you. 12 divided by 2 is 6. We need spring scales over there. Okay, everybody in a buddy? So, one of you hold that and the other one pull on it until you're registering 10 newtons of force. So, that big column of air that's pushing down on you and keeping all your particles together, atmospheric pressure, was initially measured with really primitive barometers. This is a very primitive barometer. So a barometer is a device for measuring atmospheric pressure, and the early ones were actually a puddle, a dish of mercury, liquid metal, quicksilver, with a glass column rising up from it. And what's happening here are two things. So the atmosphere is pushing down on this surface outside the tube. And then that surface exerts a force up in the tube. So if we hold this steady, if we get this steadied, and the atmospheric pressure in the room drops, then this will ease up and this column will drop. If the atmospheric pressure in the room increases, it's going to push down harder on this, and this column will rise. Now, water is not a real good calibrator for this. Mercury was much better. And we have other ways to do atmospheric pressure these days. We have a dial barometer hanging on the wall over there, and that measures in what are called bars. Torr, that's it, torrs. The original measurement was in millimeters of mercury, because they were literally measuring the height of a column. So we typically measure atmospheric pressure. The common measurements are millimeters of mercury. We'll talk about some other units. At sea level is where you get that 10 newtons per square centimeter, roughly 10.1 newtons, something like that. That's standard atmospheric pressure. And that standard atmospheric pressure, we ever so egotistically, because it's our planet and it's our atmosphere and we're the ones measuring it, called 1 atmosphere. Now that pressure reading would be different on other planets because they have different amounts of atmosphere, different masses of the planet, different gravitational fields. Some planets don't even have enough of a gravitational field to hold an atmosphere. You have to exceed a threshold of mass before you can even have an atmosphere. The moon does not have an atmosphere because it's not big enough. 1 atmosphere is standard atmospheric pressure on our planet, 760 millimeters of mercury. So the next slide, pressure, just talks about the units for pressure. And the ones that we will use most often are, in fact, and we'll talk about these if you look on 311, torrs. I like torrs. We do use ATMs. I hate pascals and kilopascals, though we use them. The units don't become as important until the next chapter where we start to do some more chemistry with gases. But you should at least be familiar with those. Okay, the very last concept that we're going to talk about today is STP, and I do not mean the automotive oil treatment. Okay, STP is standard temperature and pressure. So it's a way of designating a temperature and pressure. When we're talking about gases, we use STP a lot. And STP is 1 atmosphere, 0 Celsius. Okay? So when we say a gas is at STP, it's at 0 Celsius and 1 atmosphere. If we had a sample of gas sitting out here on the counter and it wasn't being cooled or heated in any way, could it be at 1 atmosphere in this room right now? Or, yes, it could be at 1 atmosphere. Could it be at STP? Was my question. Why? It's too hot in here for STP. It's like 21 in here, Celsius. Maybe 20. So STP is colder than room temperature. That's where we're going to stop today. On Monday, we're going to go into the gas laws, the P, V, and T stuff, P1, Z1, T1, things that you probably remember from physical science if you were paying attention during physical science. We'll make it a fairly painless review. So, okay, that's it. We will pick up on Monday.